All right, let's begin. I was going to review this, but I didn't have to rewrite it. So last time we spoke about improper integrals, and we'll talk about, let's actually talk about that now. What is an improper integral? To say f from a to b is improper, what does it mean? There are three things.
A is equal to -2.
Right, a equals negative infinity, or
b is equal to
infinity, or
f is discontinuous on the a interval.
f is discontinuous
On ab.
where?
On ab.
No.
Oh,
And
I
or.
put this in here.
And or.
If we just wrote that, is that correct?
No.
Okay.
So there's a very important distinction of what makes something improper. At finitely many points in AB. If you have discontinuities as an infinite number of points, then you're kind of out of luck as far as the Riemann integral goes. There are other kinds of integration theory that can deal with those guys very nicely, but the Riemann integral doesn't like infinite discontinuities. So for those of you who are math majors, you're going to learn different ways to integrate, and you'll be able to deal with integrals that have an infinite number of discontinuities using measure theory, the Lebesgue integral, etc. But the Riemann integral, we don't want more than a finite number of discontinuities, so that's actually important. So this is what made an integral improper. We actually saw how to actually compute it. Break the integral up, expose one bad point per integral, so any point where f was discontinuous, or if it's at plus or minus infinity, call these bad points. You break up the integral, and you take limits to approach the bad points, and you can actually compute them that way. Now, ever so often, you end up with an integral where the f of x itself is very difficult to integrate. We can't actually find the antiderivative, or sometimes we probably just don't even want to find the antiderivative. And it's not so much important as to find what the value is, but to know that it converges in general. There are going to be times when we want to know that. Does this actually converge to something? And we don't necessarily care what it is, and or the integral might be very difficult to compute directly. So we had some comparison theorems, and the second one is copied here. This was the limit comparison theorem. So if you're continuous on that interval and the ratio is a positive number, then both of these integrals will actually do the same thing, meaning they'll both converge or diverge. So the idea is you'll know about one of these integrals, and then you can therefore make a conclusion about the other one. And the idea is, of course, to compare a very simple integral that you know about to a more complicated integral that you don't know about. And if you apply this theorem, this limit, you can tell that this one converges because you know that that one converges. And we had the direct comparison theorem, which part of it is copied here. So this was direct comparison. And you have this written down like last time, so you don't even have to recopy this comparison. Which basically said if you had f greater than 0, less than or equal to g, and f and g continuous on a to infinity, then the integral will maintain the inequality. That was a property of the Riemann integral that you saw in Calc 1. And furthermore, if g converges, it forces f to converge, and if f diverges, it forces g to diverge. You can't make any conclusion in any other case, but these are the comparison theorems. So that's kind of where we left off. What I want to do now to wrap up this section is I'm going to give you a bunch of examples where I want you to actually use the comparison theorems to figure them out. So here we're going to see whether or not certain integrals converge versus diverge. I don't particularly care about the particular value they converge to, if they converge, but we just want to know, do they converge in general? let's actually do that. So here are the examples we're going to do. I'm going to do 5 of them, and hopefully we get the idea by then. So determine the convergence or divergence of. Zero to infinity of x over x cubed plus 1. 0 to infinity of cosine squared x over 1 plus x squared. Secant squared x over x squared x. One to infinity of 1 plus sine squared x over the square root of x. 1 to infinity x cubed plus x is 10 over x to the 5th plus 2x plus 1. So all of those are improper. You should be able to tell that those are improper even if I didn't tell you, based on the definition. So the goal now is to know, do these guys converge or diverge? You're going to justify your steps, but I don't particularly care about the value, so you might not want to waste your time actually trying to figure out how to do some of these integrals. Some of them are actually impossible for a Calc 2 student at this point anyway, so. So technically problem A you can do, will just be very annoying. You can do like partial fractions there. B is impossible for a Calc 2 student in case you're wondering. So is C. Pretty sure D is also impossible for a Calc 1 student. And E is very difficult. So let's actually talk about whether these guys converge or diverge. Okay, and here's where you come in. Ideas.
Compared to 1 over x squared.
Okay, why did you decide to compare to 1 over x squared?
Well, you can't, mathematically you can't really do this, but I decided to do that because I just essentially did x over x to the third, which is 1 over x squared. And x over x to the third is,
It's like 1 over x squared, simplifies to.
yeah.
Yeah, so, yeah, technically mathematically it's not really kosher, but in terms of your intuition or you want to judge, what would this guy behave like? Your intuition from limits kind of tell you, when you're going off to infinity, which is the problem here, that the bigger functions control things, right? Which means in the denominator, you have an x cubed and a 1. Who's really going to control things when you're going off to infinity? The 1 is actually not going to matter that much, if at all, right? So you can kind of just ignore all the smaller guys and just look at who are the biggest guys in the numerator, who are the biggest guys in the denominator. We're going off to infinity, they're going to be controlling everything. And so by ignoring the smaller guy, we can say, hey, that kind of looks like, you know, I'd want to compare this to x over x cubed, or 1 over x squared. All right, so finish that up. Finish that up. How are we going to actually compare that?
So 1 over x squared is a p series?
It's not a
Oh, no,
series.
wait, the nouns are wrong. You just do it the regular way you would, where you separate the bad points. So break up the integral into 0 to 1 and 1 to infinity. Set the limit of n as it approaches 0 from the positive side, of the integral of n to 1 of 1 over x squared, plus the limit of m as it approaches infinity from, well, doesn't matter which side.
Okay, so what do we know about this guy here?
1.
Converge.
That guy converges. How do we know it converges? So we had a theorem that says the integral from 1 to infinity of 1 over x squared converges if and only if your p is larger than 1. So we have a theorem. So that guy we actually know. What about this guy?
Isn't that divergent?
That is divergent. So you want to compare it to this guy? You're actually comparing it to someone who's divergent. Was that your plan?
I mean, the p series one we already figured out, but the other side's the other added part diverges, right?
Yeah.
Both of them, the whole thing's divergent.
Right.
Yeah. Making sure.
Yeah, so this is a divergent integral. Sure, you split into two parts, one of them converges but one diverges. So overall this is a divergent integral. Is that what you wanted to compare it to? Like, what was your goal? Do you want to show this diverges? What do you want to do?
I mean, yeah.
Oh, so you think it diverges? That's your intuition?
But then you can't do the direct comparison because that's less. Wait, if the greater function diverges, then it doesn't affect.
Yeah, if you make the denominator smaller, what do? You make the fraction bigger. So that guy is actually larger than this guy.
You can't do anything.
So, yeah.
Would it be not kosher to do the limit comparison and take your numerator as f of x and your denominator as g of x?
You could also do the limit comparison. What would that give you?
Limit is x goes to infinity of x over limit of x goes to infinity of x cubed plus 1, so the infinity of infinity.
So, if you took your f to be x over x cubed plus 1, g to be 1 over x squared, then you look at the limit of f over g equals, well, what would that be?
X cubed over x cubed plus 1.
Yeah, it is?
Where how did you the limit of
1.
It will actually be 1.
Yeah.
Okay, what conclusion can you make?
So if it's a positive real number, then
That's a positive real number.
it converges.
If that converges, then
So,
the original
what is your conclusion here?
converges to 1, or just converges.
What converges?
The original.
The original.
integral.
What does the limit comparison theorem say? Right? If you get a positive number,
They behave the same.
then they do the same thing. And we've already established that that guy over there diverges. You said you thought this diverges. That was your intention. Now you did this division thing to kind of justify it. So you want to say it diverges, right? Wrong. Converges. Okay, now, what went wrong? What did we learn?
Wait, where did you get the g equals 1 over x squared from?
Oh, he's comparing it to this.
Oh,
Okay, so now let's suggestion.
I have a question.
Yes.
I might be mistaken, but didn't the rules say you can only do that if both f and g are positive no matter what the x value is?
It depends which comparison theorem are you thinking about.
The second one.
The second one requires no
Okay.
inequality requirement. The direct comparison theorem has an inequality requirement. 0 must be less or equal to that, less or equal to g. The limit comparison theorem does not have a requirement. So what I'm concerned about is we came to the wrong conclusion. I want us to know why. Is the theorem wrong? Like what are we not reading here?
Wrong things compared to?
Huh?
Wrong things compared to?
No, that's a pretty solid comparison. Although it was done incorrectly. So what were the conditions of the limit comparison theorem example? Like why did this lead us astray here? What were the conditions?
G has to be continuous on A.
F and G have to be continuous on the interval. Is this guy continuous on 0 to infinity? The answer is no, which means you were not legally allowed to even do this in the first place. So that's why we ended up making a mistake, right? The preamble, the requirements and the conditions to apply the theorems are very important. Similar to how, if you're not careful, someone might guess that this converges because they see that, oh, it looks like 1 over x to the p, where p is greater than 2. But the theorem specifically says 1. Here you have a 0. You should notice these differences. The little details matter. Okay? So on the one hand, this guy was a pretty solid move. On the other hand, your interval is that you chose to compare it on needs some work. So ideas on how to fix that. Because this guy actually converges. How would you show that it converges without doing anything illegal? Yeah.
Can you compare it to 1 over x squared plus 1? Then there's a division of
Okay. So you could compare it to that. So do we know about 0 to infinity of 1 over x squared plus 1?
You should do the integral.
Yeah, but I believe we did that one last time, actually. Right? So the integral was arctangent, and it went to like pi over 2. So we actually know that converges. So here's one way to actually get to it. One way. So first of all is to note that 0 is less than or equal to this integral. And what I want to do is compare to that guy. Now, the first thing you want to know is how does this guy compare to that guy? Is he bigger? Is he smaller? Well, bigger, smaller?
Isn't the bottom one bigger?
The bottom one is bigger, why?
Is it smaller? The denominator is smaller?
Yeah, but the numerator of this one is bigger.
Oh.
You think it's smaller?
Wait. If 1 over x squared is bigger than 1 over x squared plus 1.
Is actually smaller than that guy, but it
Yeah.
doesn't tell you how it compares to this guy.
Yeah.
So what do we have here? So here, can't tell who's bigger and smaller. How do you know? Well, if I make an x squared instead of an x cubed, I've made the denominator smaller, right? Which means it makes this fraction bigger, if there was an x on top. But the fact that I turned the x into a 1 now makes it smaller. So to get from this to this, I had to make 2 changes, one of which makes it bigger, one which makes it smaller. You don't know who's going to win out. I mean, there could be ways to figure it out, but you actually wouldn't want to waste time. So, what do we do when we can't tell who's larger?
You break it into two
Plug in
steps.
a value and compare that.
Come again?
Plug in a value and compare them. Compare which one's larger at a given value.
Oh, well that's going to, but how do you know all the values up to infinity? Right? I mean, you could prove it, but I probably wouldn't want to have to do that. Yeah.
Wouldn't the bottom, can you multiply by x over x? So then it'll be x over x cubed plus x. Which,
Okay.
So then you'll know it's smaller. then the top one.
You're saying if you multiply this by x over x, which is just multiplied by 1, so you're not changing the value, you would actually get x cubed plus x,
Right.
right? Which is going to make the
Make the
denominator here
Bigger.
larger, which makes it smaller than that guy.
Yeah.
We know this converges, so getting something smaller
It's
Useless.
is useless. Yeah.
Can't you divide them?
Okay, so when you can't tell who's smaller or bigger, that is use limit comparison, right? So we have the direct comparison and we have the limit comparison. The direct comparison has an inequality requirement. The limit comparison does not, right? So can't tell who's larger or who's bigger. I mean, you might be able to come up with something like he did, but I wouldn't even want to have to waste brain energy on that. I want to compare this to something like that because this guy looks like someone I can deal with. The integral is going to be arctangent of infinity is pi over 2. We know this converges from last time. So whenever you can't tell who's larger, use the limit comparison. That's basically the idea. So direct comparison means you can tell that 0 is less than or equal to one function, less than or equal to the other function. If you can't tell, use limit comparison, which is what I would do here, right? So I would actually just now find the limit of f of x over g of x as x is approaching infinity, where I'm thinking of this guy as my f, that guy as my g. So this is going to be the limit, and it's going to be as x approaches infinity. If I take f of x divided by g of x, I will get x cubed plus x over x cubed plus 1. From Calc 1, you would know that that is 1. 1 is actually a positive, which means both integrals do the same. This means the integral from 0 to infinity of our f of x converges. So, a couple important lessons here. Read theorems in detail, because if you don't, you miss all the little details. It can leave you totally, a second ago he's like, this guy diverges. No, it actually converges. So that was the first thing. The second important lesson is, it kind of tells you when to use the limit comparison theorem versus the regular comparison theorem. The regular comparison theorem is when you actually know who's bigger or who's smaller, and you know they're both positive. Limit comparison is when you're not totally sure. So that is going to be something that you can consider. There's another way to do this one. You can actually do this with direct comparison. I guess I just want to do it that way just in case someone might have thought about doing it that way. So how would you actually pull that off if having this 0 down here is a problem? Here's one way you can do the comparison directly. Lots of varieties. Okay, so here's another way to actually think about this integral. It's the first break it up. So you can do the 0 to 1 here, plus the 1 to infinity. Okay. Now we know that this is positive. So this is positive, this is equal to that. Now what I can do is I can do my comparison on this part here. So this is going to be less than or equal to so now I can throw in this guy, right? Now, what's the beauty of that is that this part here is not an improper integral. This is just going to be some constant. It's not improper. This guy, we know, converges by theorem. So I just showed that this guy is greater than or equal to 0. He's also less than or equal to some other thing that converges. And so I can show that this guy converges by direct comparison. So a couple ways you could do both the limit comparison theorem or the direct comparison theorem. Both of them should lead you to the correct conclusion that this guy actually converges, and the devil is in the details. Right? It's going to be very easy to go down the wrong road if you're not reading the theorems correctly. Right? So you need to know the rules. You also need to know, so for direct comparison, it also requires that you're continuous on the interval, and it requires that you know who's bigger than who. Limit comparison requires that you're continuous on the interval, but it doesn't care who's bigger than who. Things like that you should know. You should also know about that theorem, the integral from 1 to infinity of 1 over x to the p. Know that converges if p is larger than 1, but the fact that it's a 1 to infinity is actually important in that. Technically you don't need a 1 as long as you start at something that's larger than 0. That's going to actually work out in your favor. But yeah, so pay attention to detail and make sure you're applying theorems correctly. And that leads us to here. So I know that's one thing students don't like, attention to detail, but it's actually super important. Whenever I give a quiz and they're like, a student's off by a little thing and they're like, come on Jhevon, it's just a negative sign, I almost had the answer. Trust me, the little things, they compound. The harder your math gets, the more attention to detail you need. You can get away with those small silly mistakes in Calc 1 and lower, but it can get you in trouble here the moment you stop reading things very carefully and knowing when you're in a situation that you can apply something. You'll get in trouble. So, that first example, we learned a lot of lessons from that. Let's try to apply them here. Okay, go.
Proposition.
Yes.
Cosine squared x, minimum value is 0.
Yep.
And maximum is 1. So I say just change the integral into 2.
That's even better than a proposition. Dare I say we can use that word that people hate seeing in a math book? Clearly. Yeah, just when you want to be like, yeah. Just shout at the reader a little bit. You should know this, and the reader. Clearly, that's true. Because we know that, we all know that cosine itself is between 1 and negative 1 and 1. So if we square it, clearly we kill the negative side, and it just becomes 0. Okay, so now what?
So if you replace cosine squared with 0, it's just 0, right? But if you replace it with 1, you get arctan of x. And I haven't really thought
Yeah, but
about
how do you actually express that though?
What do you mean? What do you mean express?
So where would we go from here? This is actually true. What can we do with this?
Instead of 0, you put the integral of 0 over 1 plus x squared, from 0 to infinity, is less than or equal to the integral of cosine squared x.
Right, so the next thing you want. So the idea is, and this is why I asked you guys to review all that Calc 1 stuff, is normally when you start with a very helpful inequality, you want to use that inequality to build up to the problem that you currently see. So of course, you don't have a cosine squared of x, you have a cosine squared divided by 1 plus x squared. So what you would do is you would divide this by 1 plus x squared. Now 1 plus x squared is positive, so you don't have to turn these equality signs around or anything. And then you can actually integrate everything, right? So that's going to give you 0 0 is less than or equal to the integral from 0 to infinity. Okay. So it's very helpful when it comes to things like this to be replacing your trig functions whenever possible with constants. And just knowing things like cosine and sine are bounded between -1 and 1 can be very helpful in this regard. So you always know that 1 is going to be an upper bound for a cosine squared. And so that allows you to start out with a bound that involves your trig function, and then you kind of build up the original function around that. So that was a technique that you learned in Calc 1 when you were doing the squeeze theorem. So that's what we would do here. Now clearly this has a nice inequality set up for us, and we know that this guy converges. We did that last time. Don't have to remember what it converges to, but you know it converges from last time. And so that means this guy converges. By, like I said, you don't have to mention direct, but once you mention comparison, people will assume you're talking about the direct comparison theorem. If you're using the limit comparison theorem, you have to emphasize that one.
Can you abbreviate it?
Limit comparison?
No, like DCT, LCT?
No.
Okay.
Okay, that's, yeah. Abbreviation is one of those weird things. Like, it's only allowed if there's like a tradition of doing it. Like, when it comes to math, those are the rules, right? If a lot of people do that, then yeah, but no one, it's not common to abbreviate those things at all. And like I told you guys before, just as important as knowing what you're doing is sounding like you know what you do. Unfortunately, that's actually important. If you have the best ideas, but no one can understand you, like what's the point, right? No one's going to do what you say. This guy sounds like a bumbling idiot. We can't take his advice. Yes, that's life. So the close to that, they'll mention limit comparison, or they'll just say comparison, as opposed to the direct comparison theorem, or the limit comparison theorem. They'll say, oh, we do this by comparison, or we do this by limit comparison. And yeah, but I don't think anyone does the DCT. It's not a thing. So that's this one. So this converged, that converged. Saw a couple ways to do this one. For this one, this is pretty much the most straightforward way, I think, of doing it. It's very hard to actually calculate that directly. It's also, by the way, just to mention, if you were thinking of doing limit comparison on this guy, it would still make sense to compare it with that, but if you actually take this divided by that, you get cosine squared, and if you take the limit of cosine squared, it does not exist, right? So I think this one is actually kind of difficult to use the limit comparison theorem with. Like, what are you going to compare to? You have to compare it to something that kills the trig function, but chances are, if you knew about that function with something that would have killed the trig function, you would kind of know about this in the first place. So I think it's very hard to do a limit comparison on this one. Whenever trig kind of shows up, your goal should be to kind of replace the trig with a constant whenever possible. Limit comparison is going to be difficult to do this with. It's much easier to just find some bound for your trig function with constants and then kind of build up around that to get to the original integral you need. And hopefully he's on the right side of the thing you want to conclude. So if you want to conclude that he converges, he needs to be in the middle, and the thing on the right needs to converge. If you want to conclude that he is divergent, he needs to be on the right side, and the middle thing has to diverge. Okay, ideas on this one?
Well, we can start off by saying, I'm not sure if this is helpful, but secant is always going to be greater than or equal to 1.
How do you know?
Because it's the inverse of cosine, so and it's squared, so we can't have negative values.
Right, so it's actually, so proposition. And this part, we call it, we won't say it clearly, we don't have to be a-holes when we need to be. So proposition, basically you can deduce that your secant squared is always greater than or equal to 1. Now, for some people who don't have a lot of experience with secant, which is understandable, it might take a while for you to convince yourself of that. But as he said, just knowing that it's the inverse of cosine should kind of tell you. If you take the inverse of something that's smaller than 1, you get something that's larger than 1 in magnitude. And so that kind of tells you. If you have here, so this is like your cosine graph here. So the y is y equals cosine x. Now, of course, when it comes to secant, whenever your cosine hits 0, your secant is undefined, so you have asymptotes here. Now, because secant is 1 over cosine, whenever the cosine hits 1, your secant is going to hit 1. Now what you realize is that your cosine will, at the edges, go down towards 0. Now, it's like you're taking something and you're dividing by something closer and closer to 0. What's going to happen is that thing is going to start to expand up to infinity. So your secant graph actually looks like this. Right. Now that's not typically something that people know by heart, so that's why I'm kind of telling you how that could actually look. So you'll notice that the secant is either 1 or bigger, or it's going to be minus 1 or less. Now the fact that we're squaring it tells you that these positive parts are going to flip up. And so it turns out that you can actually tell that your secant squared is always going to be strictly larger than 1. Okay, now, how is that helpful? Is that helpful? So if I know that secant squared is always larger than 1, what would I be able to say or do, or what do I do with that knowledge?
Find a similar fraction that's smaller.
Come again?
Find a similar fraction that's smaller.
Like?
I have already. Can you make 1 greater than 0 and then divide all of that x with x?
Yes, it turns out that 1 is greater than 0.
Well,
And then you're going to divide by that. And because we know that the secant squared is always larger than 1, then this must be less than or equal to that. And
the integrals are put in the inequality the same way.
right, so now you can throw these guys in. What can you tell me about this guy? That's 1 plus a half, so this is 3 over 2.
Is it from 0 to 1? Is it from 0 to 1? Yeah, it's from
0 to 1.
You can just integrate that. That's some constant.
Is this a constant?
Or no, that's divergent.
That's actually divergent, right? You'll see that this is divergent. And you can do that by just actually directly calculating this guy, right? That's x to the minus 3 over 2, you add 1 to the power, divide by the new power, you'll still have x to a negative power, and then you take the limit as you're approaching 0. So that guy's divergent. So the integral that we care about, diverges. radius.
What if you change
Same
that?
thing we can do with the past two examples. Sine squared x is a maximum of 1, minimum of 0.
Right?
So you set up the inequality of 2. So wait, let me.
Why don't you first change the numerator to cosine squared?
So it would be.
So you want to change the numerator to 2?
So well, you know that the numerator can possibly be 1 or 2, right?
Yeah.
So 1 is less than or equal to sine squared x less than or equal to 2.
Mm-hmm.
Then you divide everything by root x, and then you add the integral from 1 to infinity.
So do you want, so what, you're telling me that you want to say that this is less than or equal to that? Less than or equal to 2? Is that what you're telling me?
Yes.
Okay, and what are we going to do with this?
Well, you can integrate both sides of the thing we're looking for. Actually, well, we can't do anything with that then. That doesn't mean anything.
Yeah?
The first one diverges.
This diverges. What does that tell you? By the way, it means, first of all, we could have ignored this guy. Would have ignored this guy. Also, you would have kind of guessed that this diverge, why? It's 1 to the infinity of something where the top we can bound by a constant and the bottom is x to the half. So it's like a 1 over x to the p, where your p is actually smaller than 1. So my intuition would tell me that this diverges. So in the first place, I would actually be searching for something smaller as opposed to something larger. It's actually true to say this, it's just that this one isn't helpful at all. This is, of course, also greater than or equal to 0, because my radical x is going to be greater than or equal to 0 for x larger than 1. And so, call this I. I diverges by comparison. So, these two diverge. Last one. E. Ideas for this one? This is one where, this is another one where you can actually use both methods. You can do a direct comparison with this pretty easy, as well as a limit comparison pretty easy. So maybe we'll do this 2 ways, just for fun, direct comparison. Then we'll do a limit comparison. Okay, maybe suggestions, who wants to try the direct way?
1 over x.
1 over x squared? How would you? So now the question is 1 over x squared bigger or smaller than that guy?
I think it's bigger purely because you're dividing by a larger. So the numerator of the original has a single x versus 2x on the denominator.
Okay.
I have no proof for that. That's just.
Yeah, you'd have to be able to prove that.
Yeah.
That's actually not so clear. That's like a bona fide theorem that has to be proved. If you subtract something that's the same value from the top and the bottom, does it actually make it bigger or smaller? Like, when you're doing one at a time, it's easy to tell, but it's hard to tell when you're doing two at a time. So notice to go from here to here, we're changing both the numerator and the denominator, unless you see another nice way to build from this one to that one, which I don't know. That would be a nice guy to do the limit comparison with. So if you see that guy, it should be clear to you that, yeah, I probably can't tell who's bigger or who's smaller. A limit comparison would actually be nicer. So, consider the integral from 1 to infinity of g of x dx equals then take the limit f of x divided by g of x. You will actually get the limit of x to the fifth plus x cubed plus 10x squared over x to the fifth plus 2x plus 1, and that actually approaches 1, which is larger than 0. So,
And you know Jhevon converges.
and we know that this converges by theorem. So this is what I'm calling my f, and let's call this whole thing I. And so I converges by limit comparison. Okay, so that guy is a nice idea for a limit comparison because I'm not sure who's bigger or who's smaller, and for limit comparison, I don't care. How do you get a direct comparison to work out though? Ideas on the direct comparison? We're running out of time. I need to introduce the next topic, so I'll give you guys a hint. Here's the first step I would do. Moving both the numerator and denominator at the same time is confusing, so let's not do that, right? Let's just actually do the denominator, because I know very nicely how that's going to work out. What's a nice thing to change the denominator to that's going to be clear?
X to the fifth.
X to the fifth. Why did I choose x to the fifth? Because as we're going off to infinity, the biggest guys are the important ones. So what I do now is I just ignore the smaller guys, but only in the denominator. How does that make this guy compared to that guy?
Greater.
It's greater, for sure. Right? This guy is also greater than 0. Now, is this guy easy to do? Yeah? What would you do?
You can split it up.
You could split it up.
Have all powers in the numerator.
So he's literally using step 2 of our integration strategies now. Right? You can actually split that up. This would simplify to 1 over x squared dx plus 1 over x to the 4th dx plus 10 times 1 over x to the 5th dx. And we know that all of these converge by theorem. guy converged. So we had 3 convergent integrals, 2 divergent ones, but that's kind of giving you an idea. Nice mix of examples. Pretty much all the tricks of the trade that you would need to know was exhibited at some point tonight. So it's just up to you now to go find all the improper integrals you can possibly gather together and do all of them. So you get used to actually applying these tricks. A lot of times, I shouldn't say a lot of times, sometimes you can do both direct and limit comparison, and then whenever you can do that, do both ways, see which one kind of jives with you more. So then you'd always pick that one by default. That's kind of how you go about it. So, lessons, pay attention to theorems and how they apply. If there's a 1 in a theorem, it's important that it's a 1 as opposed to a 0 or something else. If you have trig functions, try to replace them by constant and then build up to the original problem around those guys. Other than that, make sure you're making moves where you know for sure something is bigger or smaller if you're doing the direct comparison. Dealing with numerator and denominator at the same time can be very tricky. It's less tricky if these were both negatives. It wouldn't be as tricky. But if you're in a situation where it's kind of tricky, chances are just simplifying the denominator alone and leaving the numerator will be useful. If the guy that you obtain is actually divergent, then maybe a limit comparison theorem can help you out there. But yeah, those are basically it. So that covers the section on improper integrals. Any general concerns, questions? So.
Oh yeah, one of the conditions is discontinuous at a finite set of points.
Yes.
From A to
Yeah.
okay.
So what makes an integral improper is the upper limit is infinity or the lower limit is negative infinity and or the function is discontinuous at finitely many points in the closed interval AB. Alright, now we're going to look at a whole other topic. It's still involving integrals. This one is going to be a lot more straightforward. But it's something that we need to know nonetheless. It's how to talk about definite integrals numerically. So essentially, we're going to look again at the kind of ideas that you applied in Calc 1 when you were applying Riemann sums. You learned about the left-hand rule, the right-hand rule, and the midpoint rule. And we're going to learn about 2 different rules that are supposed to be a little bit better than those approximations. So that leads us to 8.7, I believe, and it's called approximate integration. Some people might call it numerical integration. So if you see that phrase, it would be. And there are many more methods than the 5 which you will know by the end of this section, but these are the main 5 that you'd be expected to know as a Calculus 2 student. So, we're assuming we have a proper integral now, so you don't have to deal with infinities or a function being undefined at certain points. So we want to approximate its value for various reasons. It could be that the function itself is very difficult to integrate. So the integral from 1 up to 5 of e to the x squared dx, for example, right? So that guy's not improper, and at the same time, are you going to actually compute it, right? E to the x squared has no antiderivative. You cannot think of any function that when you differentiate it, you would get e to the x squared as a result. So if for some reason you wanted to talk about an integral like this, how would you actually go about it? How would you get to an answer? Well, that's what this guy is about. It's about numerically dealing with integrals. So we're going to go back to our roots. We're going to talk about figuring out what definite integrals are based on finding areas under more convenient shapes than the actual graph of the function. So, quick reminder. So, not going into this into any detail whatsoever, but just to kind of jog your memory. We looked at numerical methods before. Namely, back in Calc 1, you saw what's called the left-hand rule. Not very great name because there's actually a law in physics and in Calc 3 called the left-hand rule, but that's completely different, but whatever. You have the right-hand rule, and you have the midpoint rule. From Calc 1. So the idea was, you had some function under which you wanted to find the area, and what you did was you divided the interval over which you cared about into subintervals, and on each of these subintervals you erected a rectangle on that subinterval based on some predetermined paradigm based on whether the left side hits the curve, or the right side hits the curve, or the midpoint hits the curve. So the idea was with the left-hand rule, you had some curve doing its thing on the interval AB. You dissect this into like some number of subsections here, and what you did was on each of these guys, subintervals, whose length we call delta x, on each subinterval you would let the left side of that subinterval determine the height of the rectangle, and then you slice it off. Then you go to this, the left side determines the height of the rectangle. Cut it off. And this, the left side determines the height of the rectangle. Cut it off. And this, the left side determines the height of the rectangle. Cut it off. And so basically, your A was always thought of your x naught, your B was always your xn, and then you could approximate the area by L sub n, which was the summation I goes from 0 to n minus 1 of f of x sub I times delta x. And you did that, and you added up all those rectangles, you added up the height times the width of each rectangle, where the heights were chosen by the left x points. You also did the right-hand rule, where you could look at the same kind of function from A to B, split that up, and instead now you can let the right side determine the height of the rectangle. And basically, we wanted to find the area of these rectangles to talk about the area under the curve. So find the area of this, plus the area of that, plus the area of that, plus the area of that, and it was an approximation for the area under the curve. And for this one, it was your area could be approximated by r sub n, which was I goes from 1 to n of f of xi delta x. And we did the midpoint. Where the point of this one was to let the middle, which we call the stars, x1 star and x2 star, etc. And we let the middle touch the height. That determines the height of the rectangles. Right. And for this one, you could say the area was approximated by m sub n, which was I goes from 1 to n of f of xi star times delta x. And find our delta x. Right. Above, your delta x was equal to b minus a over n. That's actually still going to be true for the new methods that we're going to learn. And your xi was given by whoever the first guy was, plus I times delta x. And not as well remembered, but xi star. I mean, on the quiz, if you wrote this down, I would give you the credit. But for the midpoint rule, technically you start at x0 plus x1, or you average them, and that's your starting point, and then you added the I delta x. Alright, so that was numerical integration from Calc 1 and 5. Now, we want some new methods. Things that would converge faster. Because, yes, you did these in Calc 1 and you might have thought they were okay. Of course, you only did it for like 4 or 5 subintervals, which is not very realistic. In real life, you're going to do this for hundreds, which means you're going to be doing this for hundreds or thousands or millions of subintervals, and depending on how complicated your function is. And a computer is going to be able to do it. Now, you might think a computer doesn't actually care which one of these methods you want to use, but it turns out that for complicated functions, computation time and energy and effort actually becomes a really important thing. Those of you who are going to go into computer science will learn about that, about P and NP problems and how hard something is for a computer to do. Short of it is, you don't want a computer to do more work than it has to. So, given some function, choosing which one of these would be better for that function is going to be an important thing to consider. And maybe there's something even better than these 3 methods. And 8.7 in our textbook makes 2 suggestions. So we have some new guys here. One is called the trapezoid rule. Now, how the trapezoid rule works is it does not use rectangles at all. It actually uses, as the name suggests, trapezoids. Now, how does that actually apply? Well, on each subinterval, you're going to take where both sides of the interval touch the curve, and you're actually just going to connect them with a straight line. And so that creates a trapezoid. And so what you'll notice is that the left-hand rule gave you a gross underestimation, the right-hand rule gave you an overestimation. The midpoint, kind of almost there, but the trapezoid, the idea is the area here would be even smaller. It might give a better approximation than using a rectangle altogether. And you kind of continue with this idea for the others. You just connect the endpoints with straight line segments. Right? And you approximate it that way. Another one is called Simpsons rule. Simpsons rule decides, well, you know what? Why are we doing these things with straight lines anyway? Don't we want to approximate the area under a curve? Why not use a curve? So the idea behind Simpsons rule is, if we have a curved function, let's actually approximate it using curves. So what it does is it actually uses parabolas. So what it would do is it would take 2 subintervals at a time, find where those guys hit the function, and then it will actually draw a parabola through those 3 points. Then it would find the area under the parabola. And then it takes 2 more subintervals, and it creates 3 points with those guys. And it would create another parabola connecting those 3 points. And then it will try to find the area under that parabola. Right? And so the idea is the parabola is going to fit something that's very curved. even better than any straight line approximation would actually fit it. And so what we're going to do is we're going to look at these two new methods. Now, I have handouts that tells you what the formulas for approximating these guys are, and I'll just give them to you. Next time we're actually going to derive where these formulas come from, because you're going to have them memorized. So I figured showing you where they came from would actually give you a good intuition on actually memorizing. It would help you in memorizing the formulas. But once you memorize the formulas, it's not going to be that bad. Kind of like the midpoint and rule and all that stuff. It's just kind of plug and chug. You just kind of plug in the numbers in the right places. There should be more than enough for everybody. Pass my binder. Alright. So next time we'll pick up proving these, and then we're going to do actually the example on the reverse side of that.